Okay, lesson 1.4, discontinuities. So yesterday was continuity. So in order for a function to be continuous, 3 conditions need to be met. So a function is continuous at, let me start this over here. Continuous at a value, okay, so discontinuities only happen at specific values for x. If first, the function exists, f of c exists. Second, the limit exists, so the limit as x approaches c exists. And then lastly, when the y value of the function is the same as the y value of the limit. All right. So now let's talk about discontinuities. Discontinuities occur at domain restrictions. So the first thing that you're going to do whenever you're asked to determine if a function is continuous or not is determine the domain. So being able to look at a function, understand the restrictions, and find the domain is very, very important. 2 types of discontinuities, and you did study these last year. Removable versus non-removable. So removable discontinuities graphically would be a hole. Non-removable discontinuities graphically can be jumps on the graph, vertical asymptotes, or holes as well. The difference is right here. This is the calculus of it all. The existence or non-existence of a limit. If the limit as x approaches c exists, then the discontinuity is removable. If the limit as x approaches c of the function does not exist, then the then the discontinuity is non-removable. So, for examples here, determine if any discontinuities occur, label them as removable or non-removable. Okay, so when I look at these functions individually, x squared, domain of that function is all real numbers. My linear function x, the domain of that function is also all real numbers. So the only place that a discontinuity could occur is where the domain switches. So we're looking at x is equal to 1. So first are 3 conditions. What is f of 1? Okay, so f of 1, I plug that into my quadratic. The y value is 1. Now to find the limit, because it's a piecewise function, I have to look from the left and the right. Limit as x approaches 1 from the left-hand side, that's all values less than 1. So I plug that into x. So limit from the left-hand side of 1 is 1. Limit as x approaches 1 from the right-hand side, that's my quadratic. So that's 1. So by definition, the limit as x approaches 1 of my piecewise function is 1. These 2 values are obviously the same. F of 1 equals the limit as x approaches 1. So what is our conclusion? That the function is continuous everywhere. And to write the domain for all real numbers in interval notation, we would write it as -infinity to infinity. All right, so another piecewise function. Individually, the domains of each function are all real numbers. So we do not need to concern ourselves with anything other than the changes in the graphs. So we're looking at x is equal to 1 and x is equal to 2. All right, so we're going to go through the 3 points for each x value. F of 1 exists. I plug that into my linear function. F of 1 is equal to 9. The limit as x approaches 1 from the left-hand side, that's all values less than 1, I would plug into x squared. So I get a y value of 1. The limit as x approaches 1 from the right-hand side, I would plug into my linear function, 10 minus x, and I get 9. Since the one-sided limits are not the same value, our conclusion, the limit as x approaches 1 of the function does not exist. Now remember the directions, label the discontinuity as removable or non. Because the limit does not exist, this is a non-removable discontinuity at x is equal to 1. All right, let's look at x is equal to 2. F of 2, I plug that into my bottom quadratic. 12 minus 4 gives me a y value of 8. Limit as x approaches 2 from the left-hand side. I plug that into my line, 10 minus x. I get a value of 8. Limit as x approaches 2 from the right-hand side. That's my downward facing parabola. That's also 8, and I know that because I found that up here. So these two pieces of information tell me that the limit as x approaches 2 is 8 as well. And I know I'm writing all the steps down. So f of 2 equals the limit as x approaches 2. So what's our conclusion? It's obviously not a discontinuity, so function is continuous through x is equal to 2. All right, x over the absolute value of x. So this is now the second time we're seeing this graph, and it's very, very important that you're understanding what it looks like. So just to recall, absolute value of x is defined as a piecewise function less than 0. When x is a positive number, the absolute value doesn't do anything. The positive number stays the same. So if what's inside the absolute value bars is a positive number, then that just remains exactly the same. If what's inside the absolute value is a negative number, then the absolute value takes the opposite of that number inside. Okay, so now if I add my x divided by the absolute value of x, okay, so I'm just taking x divided by x would give me 1 for all values bigger than 0. And it would give me -1 for all values less than 0. And remember from our last set of notes, I can't equal 0 because my domain restriction is that x can't equal 0. So when I go to, we can stop right here. F of 0, direct substitution gives me 0 over 0. Even though that's in indeterminate form for the limit, that tells me that my y value does not exist. Okay, so I know that the discontinuity occurs there. But now when I go to see if it's removable or non-removable, I have to look at 0 from the left and 0 from the right-hand side. So 0 from the left-hand side, the limit would approach, I would be looking at -1, so that limit is -1. The limit as x approaches 0 from the right-hand side, that limit would be +1. So from here, because the limit does not exist, this would be a non-removable at x is equal to 0. Okay. Then the last one, so first thing I'm going to do is determine the domain. So the domain of the function, when I look at a rational function, I'm sorry, I don't know why it keeps doing this. I look to see what values of x would put 0 in the denominator. So when I look at the bottom, that factors to x minus 5 times x plus 2. I'm going to find where they equal 0. So 5 and -2 are my possible places for a point of discontinuity. And in this case, there's definitely going to be discontinuities. We just are going to determine if they're removable or non-removable. So the first thing I'm going to do, I am going to simplify f of x. So f of x, since the denominator is factorable, and that factor matches the expression on the top, f of x now simplifies into 1 over x minus 5. So let me reiterate. I already know that 5 and -2 are discontinuities because those values are going to put 0 in the denominator. I'm not allowed to divide by 0. Now what the goal is to determine if they're removable or non-removable discontinuities. So at x is equal to 5, then what I need to do is determine if the limit exists. So when I go to take the limit as x approaches 5, and I can use the simplified function, I get 1 over 0. This is not an indeterminate form. 1 over 0 means that the limit does not exist. And graphically, that means that there's a vertical asymptote at the line x is equal to 5. So x is equal to 5 would be my non-removable discontinuity. So then at x is equal to -2, I already know that f of -2 doesn't exist. When I go to find the limit as x approaches -2, and again, I can use my simplified function, I do get a value. So when I plug that in, I get 1 over -7. So since my limit exists, this would be a removable discontinuity. And graphically, there'd be a hole on the graph of that function. Okay, so last thing I'd like you to do, we will talk about this in class, intermediate value theorem. If a function is continuous on a closed interval, so x can equal a and x can equal b, and some value k is between the y values of the interval, okay, so k is between f of a and f of b, there exists at least one number in C such that f of c equals k. All right, so what does that mean? Let's just say I have any function here, any continuous function, and that's really important. So no matter where I start, I draw any type of continuous function, okay? Here's A, here's B. So this value here would be f of A, and then this value up here would be f of B, right? They're my y values there. Then as long as k is between these values, so k has to be between f of A and f of B, so this will be k. Notice here that there has to exist C between A and B such that this point exists. So my x coordinate is C and my y coordinate is k. So where that horizontal line intersects the graph of my continuous function. So what we'll talk about in class, this theorem is very important, and it verifies that the zeros of a function exist. Doesn't necessarily give us the means to find the zeros, but we are able to verify that zeros or x-intercepts of a function exist. Okay, that's it for today.